this is the key idea, key thought that you should learn from this presentation, that irrespective of how hard or how complex the problem is, whether it's some kind of complex RAG, or complex SEC-like documents, or nested products from e-commerce space, or legal documents, essentially about finding the right representation and the bridge operator. Different representation, different bridge operators work in different cases, and the strategy that you have to choose. Whether it's information retrieval or RAG or deep research, the core problem is the art of matching. How do you match the query with the documents? What is the strategy that you use to match the query with the documents? Documents can be messy, long text, PDFs, some figures and tables, and so on. Query is generally short sentences. And matching lets us retrieve pieces of knowledge from a subset of the document that put together, will answer the query. The answer may not be in a specific place in general, but if you find the set of relevant documents, then you can extract the answer to the query from them. So the retrieval quality determines how good an answer you get, and it turn depends on how well do we match the query with the what is the strategy that we use. And there could be, the complexity arises because there could be several strategies that you could use for a given query, and the issue is that we don't know which strategies to use, and if we try to use too many, generally ends up being a mishmash of several strategies where we don't have a clear idea how to select the correct strategy. So to understand why matching is hard, the core issue, the key issue is that similarity means different things to different people. It could be just exact words, or it could be just paraphrases, or it could be same keywords occurring at different places, semantic meaning, or it would involve word knowledge. It varied from person to person, also something that appears similar for one person may not be. So there's no single notion of similarity, and the task of matching must capture the right notion of similarity for a given audience at any time. Okay, so you have to devise a strategy that satisfies the particular audience notion of similarity. Okay, and if you make our definition of similarity too narrow, well, let's look at an example. So when matching is easy, a narrow notion of similarity. The happy case is when there is keyword overlap. So the query is t-shirt and the document mentions the phrase men's t-shirt. So exact string overlap works there. You can do a simple keyword match, find a t-shirt in the document, and just collect those documents and present them as results. So this is the simplest case, the easiest case when matching is very easy. We have defined a very narrow notion of similarity. Okay, a harder example here. Query is, in which forest do we find an orangutan? The document, one of the documents says, orangutans are native to forests of Indonesia and Malaysia. Okay, so orangutan, orangutans. Query mentions orangutan. Document has the plural. Again, forests, plural. But there is an overlap modulo, lowercasing, and stemming. So what we need to do is to transform the query and document into a representation. Now, representation is the key concept that I want to motivate in this video. So first we learn about representation, then we learn about bridges that connect the representation. So what do you mean by representation in this case? Representation of query is the forest, find, orangutan. These three keywords are key to the query. Okay, and note that they are singular, forest and orangutan. D is again number of a native forest orangutan. We have done lowercasing and stemming and remove stop words to get these two representations. And once we have this bag of words representation, then we can look for exact word overlap among these bag of words. In this case, there are two keywords that exact overlap, and so uh, we are able to match this query with the document. So now generalizing a little bit, in the first case, it was an exact overlap of t-shirts. It was easy. In this case, there's no exact forest. There's no word forest. It's a plural of that, so there won't be an exact string match. Um, so to generalize to more complicated cases, the two concepts that we need to understand. One is the representation. So what we did in this case is to find a good representation of query, which and the document. And once we found that, there was a way to bridge these two representation by using the exact word overlap operator. Okay, exact word overlap, string overlap over bags of words. And so that's our strategy. And we were able to see that if we choose this representation, then we can use the familiar word overlap operator to get to bridge representation. And if we bridge, then we find, so whatever document the query bridges with, those are the relevant documents. Okay, so finding the right representation and bridging strategy, bridging operator gives us all the relevant documents. So information retrieval, the core matching problem is about finding a representation and a bridge operator combo. Okay, and this is the key idea, key thought that you should learn from this presentation, that irrespective of how hard or how complex the problem is, whether it's some kind of complex RAG, or complex SEC-like documents, or nested products from e-commerce space, or legal documents, essentially about finding the right representation and the bridge operator. Different representation, different bridge operators work in different cases, and the strategy that you have to choose. Okay, so how do we, so just making that very, matching is representation plus bridge. This query, you can imagine a query on the left, document and the bridge connects that representation. Okay, and we only match the representation of Q and D. And I'll give examples of representations, different kind of representation, to make it more precise, this abstract notion. And I'll have other videos also that help. This notion of representation bridges helps explain several other strategies that you might see that might make the whole world of RAG or information retrieval seem too complex. Looked at an example where exact keyword matching breaks, but we are able to solve it in the earlier case by using the stemming and the lowercase operators, and then we are able to bridge it. But here's an example, a variation of the previous one, where that the previous strategy also breaks. So in which forest do we find large monkeys? Document has orangutans native to rainforests of Indonesia and Malaysia. So there are no large monkeys. There's no monkeys in the document. There's no forest is not mentioned. Rainforest is mentioned. So there's no, even if you stem the word, it's very hard to bridge forest with rainforest, large monkey with orangutans. So the keyword bridge fails dramatically here, and the failure is not in the data, it's actually in our representation. So we need to come up with a smarter representation to bridge. And what works in this case is what is called semantic search. Okay, so we choose a representation which is a semantic representation of query. It's not the exact words, it is a representation in the vector space as a list of numbers, Those long, no, the list means a special thing, capture the semantic meanings. The dimension of that, the elements of the list capture the semantic dimensions of or the meanings of different kind of meanings of that word in different contexts. Okay, so you choose a representation which is a semantic vector. Now these two vectors are of same size. There are different ways to map the text of words to this vector representation. But if we do that, then we have representation of query and document. In this case, this is the query. We map this to a vector and the document one. And the vector captures the meaning of orangutans and rainforests. And when you go to the meaning space, you can see that large monkeys are similar to orangutans and forests are similar to rainforests. So that's why we chose that meaning space, and these vectors are how we represent the meanings of this, at least one way of represent the meaning. Okay, so uh, we get these vectors, and then once we have these vectors, which are mathematical objects, we can use cosine similarity between these vectors to find if the query and the documents are related or not. Okay, so cosine similarity is tells you how close these two vectors are in the angular space, and 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 if it is if the vectors are close, then and the value is high. In the other, so as having a single vector is the default way of representing the meaning. You could also have multiple vectors corresponding to different words in the query or the document, and then you'll have multiple vectors on the query side, multiple on the document side, and then I use something called maxim or the Colbert representation to do the matching. Okay, so the essential idea is that you have to choose the representation here, whether you choose single vector or multiple vectors, and then the operator, cosine similarity operator or the maxim operator to get the to match the relevant. So that's how we had an example where keyword similarity failed, but having these meaning representations allowed us to again go back and find similar documents. Okay, vectors are generally there's a lot of research, more than a few decades of research gone into representation of words and sentences and paragraphs and documents as vectors, meaning vectors, and the very interesting properties of them. Now, zooming out, uh, there's no single when you're faced with a general information retrieval or RAG problem, and deep research in turn relies on several parallel RAG runs. When you face with a real life problem, there's no single bridge. You might think that meaning, if you choose a meaning representation, you've captured it. But the way it is constructed, because of the way it is constructed, it loses details about the keywords that will involved in the query. So you have the meaning of the whole thing, but you don't have precise details about the keyword. And there are ways to get it back, but then again, you have to switch to representations again. So there's one place where you have keywords and exact match, and the place you have meanings of vector, meanings of blobs, and cosine similarity. And these are sort of two extremes, and both are important. In some cases, you need exact match. For example, e-commerce space, or in medical domain, we need exact term matches, and there are cases where you just need meanings of blobs to match. And so both of them are used, and what is called a hybrid search is combines these two representations. So combining is another topic. You have representation bridges, and then if you have multiple bridges, in which one bridge over the keyword representation, other bridge over the meaning representation, then you have to merge or fuse them uh, in some way so that you get a single score of similarity or a single representation, whichever way you go, and um, and then use that to find relevant documents. So that there RRF, for example, is a strategy to fuse, and there are many ways to merge the result lists also. Okay, so that's the key idea. You have to choose the representation, choose the bridge operator, and you might have to use multiple bridges and fuse them for solving the practical RAG problems. You would even think of it as every bridge solves a particular problem, but then creates another. You have to combine it with another bridge to get a holistic view, and that's where a lot of tricky stuff happens. So, to solve a practical problem, the core questions are: given a query document context, which representation bridge works best, or which combination of representation bridges work best? If you have multiple bridges, how do we combine or fuse them? And more bridges lead to more issues in combining them. People try to weight them by assigning scores, higher weights to one bridge versus another, and those are manual tweaks that some cases work, but people go down the rabbit hole of tweaking these weights manually for a particular system to work, and that's not a very elegant solution, and there's a lot of human labor involved which we want to avoid. So keeping it simple, having a few set of bridges over a few set of fields is often the key to having a robust RAG system, irrespective whether it's text RAG or multimodal vision RAG or video RAG. So these are the key problems that you need to strategize to solve. What is other representations? Generally, people start with the keyword and vector representation both, and get results and then rank them, re-rank them. So yeah, I'm not sure I'm talk about re-ranking, but re-ranking is also a kind of bridge over uh, where you use neural models to bridge um, a selected set of documents from the previous phase to align with the queries. It just defines a uh, new way to do new representations to bridge. Uh, so what happens in practice is a you have a bunch of bridges, you get a bunch of results, and then you apply another set of bridges, and then you get a set of re-ranked results, and maybe there's another phase, or there's a cascade of these bridges that actually works in practice. And I'll have more practical examples and concrete explanations of this. I am trying to just give the abstract, yeah, go to the abstract view of it. A little bit mathematically, if you want to understand, a bridge operator involves query, set of documents, representation of query and documents which you have chosen, how to get it. The uh, essentially use a similarity operator, that's the bridge similarity operator, to match the represent query and the documents. And query, it could be just bag of words, or it could be a vector representation or multi-vector representation, and there's a similarity defined over that. And once you get these, this gives out a scalar score or a number, and then you can rank each document by the number that you get by similarity, and so you get a ranked list of documents for this query. And if you have millions of documents, you clearly don't want all of them to be listed, so you need to define a cutoff. So below that threshold, below that, some kind of threshold. Again, thresholds can be defined in many ways. You can just say that I want top K. Below 10, I won't look. Or you can define a score, which is a more dynamic threshold. Below the score document, I won't look. So bridge essentially gets you a rank list with a cutoff. And that's the output of this operator if you apply this on queries and set of documents. And once you get this list, you can again frame that list as a set of documents D, and apply another bridge on it. Okay, so this formulation found bridge the notion of bridge to be crux of solving, instead of sort of hand waving through the solutions. If you think in terms of bridges and representations, it makes it enables you to think more systematically and in a modular fashion. Makes information retrieval, solving IR problems more composable. Um, and and so eh, I'd like to, if you have worked with such problems, I'd suggest you go back and think of them again in terms of representation bridges, and how uh, and see if it makes it far more clear, the strategy, the solution that you chose to use, and make it work. Um, and I'll just finish with the final insight that uh, solving RAG problems is iterative. It's like puzzle solving. So you don't know the best representation bridges in the beginning, and so you pick some, you observe the results, you do evals, on the whole pipeline. And then you observe that these are the queries that are missing, and then you go back and think what are the representation of bridges that will make these queries go through, and the earlier ones also, without breaking the other ones. And so there's a co-evolution of representations, bridges, that happens when you're solving a RAG problem or a deep research problem. And um, and that's what makes it both hard and fun. So yeah, that's the overall. Uh, that's my introduction about representations and bridges. Uh, this is the core of IR and RAG problem solving, and I suggest you to yeah, think more about it, and map, if you solve problems earlier, map them to the notion of bridges and representation. And for deep research, there's to answer queries which are not uh, sort of narrow, which are, or to answer queries which are far more broad and involve searching through several documents and multi-hop and so on. The solving those queries involves query decomposition, solving splitting down queries into several subqueries, subtasks, and then and iteratively solving them, or solving them in parallel. And so when you go down to the lowest subtask, you use the notion of bridges to solve them. But once you have found these relevant documents, there's a way to combine them through different subtasks, and that's the challenge of deep research. I'll talk about that in some other videos. So I hope you got something useful to learn from this video. I again urge you to think about your RAG problems in terms of bridges and representations.